So I will draw this one more time, but this time we're going to, instead of picking another point BF of B on the curve, we're going to allow that location to be variable. We will not select a particular value, B. So again, the curve looks something like that for the most part. There's f of x. Again, a was around here somewhere. And there is, again, a, f of a. All right, so now instead of picking b, a particular value, I'm going to pick nothing in particular, but just the variable x. Okay? And I'll map this up to the curve. Well, of course, that is nothing other than just the symbols x comma f of x. For any x I would pick, that would be the x and y coordinates respectively. Okay? So we want to get a hold on the tangent here, because the tangent slope is the same as the curve slope by mathematical definition. To do that, we're going to use the secant slopes. Try this. The secant slopes, those average rates of change, that far. So again, the slope of the secant, hopefully you can see that, slope of secant is now given by the difference in the y values over the difference in the x values, where x and f of x were left variable, for a reason we'll say in a second. And that is, what I want to do now is, certainly this slope is not this slope, but there's a relationship between them. And that is, if we were to move x closer to a, right? So now, let x move closer to the location of concern, right? The location where we actually want to know what the slope is there. Move x just a little bit closer, what would happen? So this second point that I drew, right, if x moves this way, then the function value is moving down the curve here. So let's say we just move to here, for instance, right? X moves over there to x, so then we map that up here, and we have a new point. It's still x f of x for whatever x I picked, right? Something closer to a, but I have a new, of course, secant line there. Okay? A new secant line there. And that new secant line slope is closer to being the slope of the red line, of the red tangent line. And as x gets closer and closer, again, that will yield another new secant line with a new secant slope, which will be getting closer and closer to acting like, to becoming the slope of the tangent line. So therefore, it seems like if we let x approach a for the slope expression f of x minus f of a over x minus a, if we let x approach a for this expression, then in theory, right, it should get closer and closer i.e. approach, right? Maybe even converge. It should get closer and closer to the slope of the tangent line. Which is the slope of the curve. So therefore, this basic limiting process, as x approaches a, for this slope ratio should converge to the actual slope of the tangent, which is the slope of the curve. But in this section, we will only compute that through approximation and guessing.